get off here.
Okay, sounds good. I'm on mute.
Good morning, everyone. I'll give everyone a second. It looks like we've only got Tondra, you're the one on the call here at the moment. So we'll give folks a second to join in. All right, well, I guess we'll start to an audience, small audience here now. Hopefully there's just a bunch of stragglers be coming in, and we're going to be recording this as well anyway. So good morning, everyone. My name is Kevin Grover. I lead the customer success team here at Looq, and welcome to our next edition of the webinar series here. So this capture or webinar is going to be on capture workflows for linear survey projects. So this is going to be specifically for like roadway infrastructure projects, any type of corridor project where we just need to take into account a few different things when we're actually doing the capture and the processing. So just to dive through here, an intro to Looq, if folks aren't familiar with our platform just yet, and the recording that's going to come out is we are a handheld photogrammetric survey capture device. Our device is called a QCam, which is a 4-camera system. It has a GNSS survey grade system on it, as well as some onboard processing. Allows you to do quick mobile capture with a handheld device as you're walking. Our processing platform is called QAI. That's kind of the brains behind it. That's what allows us to do the cloud-based photogrammetric processing. It fits the data and it generates a 3D point cloud from the data set there. Our QApp application is our web application that allows you to upload, navigate, view, manage, and export data. We've got some other tools in the web app application as well too that allows you to work with the information. But this is kind of the platform overall, and we're always adding more and more features to our product as we go. Quick overview of how the platform works. Like I said, we are a survey product as well, so it allows you to use a local base station or a network station, whether it's a core station or a SmartNet from Leica, etc. It allows you to generate, use GNSS corrections to correct the data as you're walking. It's a handheld system, so you're collecting and walking around. We're basically painting the data that you're looking at collecting with the device. So we can do curb and gutter, ground-based projects, roadway projects, linear infrastructure projects, all of this data that can be captured from our handheld application. In the office, how it works is we are fully cloud-based, so the data gets uploaded after the collection. It's uploaded to your cloud account, and that's where you're able to generate the 3D data product. We've got workflows for survey to align to control. We've got some other tools for extracting data, and then we've also got the features to allow you to export these products to a third-party application, and you can use it in a Civil 3D, Bentley, TBC environment, really anywhere externally. So now to the meat of the webinar today is we're going to specifically talk about linear survey projects. This is going to be, like I said, for roadway projects, long linear capture projects, and how we want to allow you to work with the data to collect it efficiently and process it so it's going to get an accurate data set in the end. So one of the first things, of course, is kind of pre-planning your corridor capture. So for linear projects, this is definitely where we want you to do a little bit of planning ahead of time. So long projects are important to split up into tiles. So ideally, what we're looking for, I'm going to click through here, is if you have a longer linear project, we do want to separate it into chunks. The reason for that is because we do have a maximum capture length for a data set. So we want you to get basically individually processed data sets for each of the captures. That will allow us to generate the best, most highly precise data for each of those collections individually. And then we're able to string them together with the PPK processing and also your ground control workflow afterwards. So it's important out of this is to make sure you do have overlap between your sections. That just allows us, again, where you're going to be stitching together, we can get accurate data in each of those areas and make sure you've got complete coverage. Because we also do fit each data set to its own ground control, that's where you do want to have overlapping ground control between the two captures. That way, at least they're going to be linked down and fitting as close as they can between those data sets together. And then the other best practice, of course, of adding your checkpoints in between. From the survey side, it's definitely necessary to have both survey targets and checkpoints. The checkpoints are just independently used in the adjustment, And so you can use it to just validate the quality of the adjustment after it's all processed together. So that's how we want to start splitting it up for doing longer corridor capture. We are looking at extending the capture length over time and doing some other ways of adjustments, what I'll talk about in the end for a couple limitations we've got at the moment. So because we do rely so heavily on PPK GNSS corrections externally, this is where the best recommendation we have is make sure that you are running a local base station. So a local base can mean a number of things. That can be you downloading corrections from a known correction service that's just nearby your project. So whether that's from a course network, maybe it's a DOT that's got a public network available, you still have control over what, the Rhinex data that comes out of that network. There's paid networks from SmartNet, from Trimble, TopCon, etc., that you can download base station data and use that in your correction service. So you have a bit more control over that as well. And then the third one is also your own user provided base station data. So if you've got a base station, whether it's a Trimble, like a MLID, really any base station that can capture a static file, that's where you can upload that and use it as a correction service. So the benefit of doing a local base or from one of these providers is just that you have control over which one to use. This is very traditional for like PPK, RTK. The shorter the baseline, the better the residuals, the better the results will be. So you have the highest probability of choosing like a fixed correction position out of it. So that's what we're looking for when running a local base. It really helps out our linear projects in that case. So all we require is a 1-second Rhinex. It's a zipped version of the Rhinex, and that's all done actually post adjustment. So you just need to have time overlap between your base and rover, the rover being our QCam, and that allows you to use the correction services in the processing. The next one, of course, like the setup ahead of time, is also using ground control points. So we do rely on these as well. There's no way that we can validate the quality of your data without you having something to validate it to. So control points can be really anything. They can be painted targets. They can be mag nails you put in the ground. They can be a lath you put in the ground, or even anything painted. It can be on walls or ground. It really doesn't matter. And of course, they're surveyed within your accuracy specs. If you're surveying it to conventional survey quality, that's awesome, because then it just allows us to basically fit it to like most precise data we have. If you're using RTK, make sure you're just not putting targets under trees, around buildings, because we are going to fit to whatever control points you put into it. So the goal out of this is really necessary for nailing down that absolute geolocation and also validating the errors of the adjustments as part of the processing. The next stage of this is, of course, where you put those GCPs does matter. So specifically for like a linear corridor project, we want to make sure you're putting them in the right spot. So in our case, we need a minimum of 3 GCP points per capture, and that is because we just do a rigid body transformation in the workflow. So we're basically taking a minimum of 3 points and adjusting it to best fit a plane to your data. So we are scaling, rotating, and translating the data to fit, but we're not correcting for any distortion inside the data. So best practice out of this is avoid 3 points at a line, because that's where you're gonna have errors of rotation. If you have 3 points just in a line, your errors will get larger as you go out. The goal of this is have your GCPs at the extent of the capture. So in this example here, I care about the features that are on the road itself. That's why my control point is at basically the extent of the roadway to the sidewalks. So then I'm really just worried about the data inside of that green kind of polygon I'm showing there. It's going to give us the highest precision data. As you go out, there might be some more error that gets introduced just because of how the best fit plane is being done. I recommend, 4 to 5 GCPs, extent of the site, extent of the capture, and then you have additional points in between as check shots that allows you to basically validate the quality of the adjustment. The next we're going to talk about is, overlap. Like, how much data do I need for doing a collection? So best kind of scenario around this, because we're image-based, we're photogrammetric-based, is low density data will, of course, result in a lower quality and less accurate data. So what we are looking for is a lot of overlap. This case, the example is just kind of an example of how you would typically walk kind of more of a linear project. It's nice to walk along curb lines of the roadway. The benefit of this is, of course, it lets you not enter traffic. So in their case, we're actually just walking around curb lines, walking along sidewalks, but then we're also doing some circling around and the walking back and forth. Because we're imagery based as well, because we're walking in one direction, we do have 4 cameras, so it's taking pictures of what it can see. But if we walk backwards in the opposite direction at a bit of an offset, that helps because then we're basically able to see data from different positions as part of it as you're walking in these parallel lines. So the more overlap you walk, the more dense the data is going to be, the better reconstruction can be. So in the case of doing a roadway, it is beneficial to at least at a minimum walk down the one side of the curb line, walk down the other side of the curb line. If it's a wide roadway, that's where if there's a center median, ideally you can walk that center median as well. If there's sidewalks adjacent, if you can walk those, that's just going to increase your density and overlap in general. So the goal of this is break down into your area of what you can do in the set period of time. So this will come out of like how once you get playing with our system and figuring out how much you can collect, is you can see how much data you're going to be able to capture. So the capture time with good overlap coverage, we can do up to maximum 30 minutes of capture per data set at the moment. I'd say only do that if you've got really good GPS. So if you're working on a roadway like this, where there's some little trees scattered, the buildings are further away, we're basically going to have really good GNSS data for the majority of the capture. That's okay to push up to the 30-minute mark. When we get down, if you got limited GNSS, that's really where we do want to make sure that you maybe kind of don't push the limits of the capture time at the moment. We're working on some adjustments to our algorithms now, but the reason around that is that just if there is any fluff in the data, if you don't have good overlap in some areas, it can tend to introduce some distortion. So until we're able to do a non-rigid adjustment, stick to about 20 minutes if you've got a limited GNSS. If you have good GNSS and good coverage, then you can basically push that up to half an hour. But the key part of this is, yeah, high overlap does just result in better reconstruction overall. The next part we've talked about in all of these different webinars, I'll kind of mention this here again, is the benefit of the way you walk does kind of matter. We get our best collection when you don't walk just directly in a straight line. So as you're walking these parallel paths back and forth, try to add a bit of an S pattern to your swagger, to your walking path. What that does is that actually changes the orientation of the imagery in all of the cameras and allows us to just do a better reconstruction because everything's kind of changing. Adding that little side to side swagger, and you don't have to do much. It's like kind of a foot or two back and forth. That just allows us to basically get some different angle that it's in different parallax, the objects that we're basically trying to measure to. So that does actually really, really help the reconstruction. It just helps us, especially with vertical features. It does allow us to reconstruct a little bit differently just because we are entirely photo based. So called it a Looq swagger. It just allows you to kind of navigate back and forth a little bit, and it'll get you to collect a little bit of a different way. But no matter what you collect, whether it's a power line, roadway, a site survey, it doesn't matter. Add that little swagger to your walk. In all cases, your data just ends up being a lot better. The last one is kind of just, in general for just really any like survey type workflows is loop closures are our friend. So no different than doing like conventional survey. If you don't, if you're doing a traverse, you don't want to have open-ended traverses. Like the reason around that is you just got hanging loops that we just really can't, confidently adjust everything if you've got a hanging loop. So the goal of this is try to get loop closures as much as you can. So for this exact example I was showing before, you can loop around back and forth, but if you can close off your loops where it's safe to cross the roadway in certain cases, that's super beneficial to us because it allows us to just really tighten up the loops on the two ends. But we do want you to do this in the safe location. So this is all part of that pre-planning effort you want to do ahead of time, is how I can take my data set and split it into sections to A, fit in with that capture time that I'm able to do, and B, able to fit my ground control where I need to be, and also to allow me to, safely cross the roadway in locations that, again, are just safe to do so. We want to make sure that we're avoiding you walking across the roadway if we don't have to. So the challenge when we don't have loop closures is you can tend to kind of get some drift in your data just because we may or may not have the proper overlap, or maybe we're lacking some GNSS in some data, then it might produce some drift into it. But tightening those loop closures really just helps tighten up the entire adjustment in the end. So I like this kind of comparison. A lot of people that are comfortable with our system or comfortable with flying a drone is really kind of the best workflow that I can kind of introduce is capture it like you're flying a drone. Is we do want the back and forth passes typically that you would with doing with a drone. It allows you to just get your overlap back and forth. But then when you've got areas that you care about, that's where you want to be able to actually circle around objects. So in the case of a linear project, most of it's going to be the long linear paths back and forth, but maybe there's like a sign feature, maybe there's some transformers, maybe there's like kind of some nooks and crannies you want to get into. You do want to basically do more capture in those areas. That just allows us to get more imagery for the data you care about. So back and forth captures like a drone, circle around like doing say like oblique flights with doing a drone, all of that's combined together in our processing algorithms, and then we're able to generate just the highest density, most precise data set that we can get in the end. So just a really simple rule of the thumb. If you compare it to that, it's a really easy way to train some of your field staff to do the best capture that they can do. The next one's here is just challenges that we've got for doing linear projects. Not every site is going to be conducive to using our product, as well as even just how photogrammetry kind of will generate a quality data set. So this is one of the examples that's it's a bit of a challenge to basically do a really highly precise survey of a roadway like this. And the reason for that is we're lacking vertical features in the data. Sure, we've got the roadway adjacent to, we've got some fence posts, maybe an overhead power line, but the challenge with it is that we do rely on vertical features to reconstruct properly. So this is really where any like SLAM LiDAR system will fail miserably in an example like this. With us, we're still going to be able to generate a data set, but because we're relying on image matching and that texture matching, it becomes a bit more problematic to generate things like this. So I'd say if you are going to be doing sites like this, increase your overlap. We might need you to zigzag back and forth down the roadway, but it's going to be a challenge to basically get a product like this really precise, purely just because we're lacking some of those vertical features. Other scenarios where we can have some challenges is if you've got captures with limited GNSS, like take an example, this example for an instance, if for some reason we had poor GNSS, the problem is that our photogrammetric algorithms kind of kick over and do when we weight them more heavily, but we've got poor GNSS, but we're going to have an issue with trying to feature match an environment like this. So not every linear project is going to work well with the Looq capture. If it's a rural roadway, we're going to struggle. If it's more of an urban corridor with buildings adjacent, curb and gutter, there's vertical features for powers, poles, that kind of thing, we'll reconstruct really well in those dense urban environments. But challenges like this are going to be tough. The last challenge we have, of course, is your GCP placement. If you do too long of a collection, let's say we've done like something this long, my control points might be very close together at the two extents. The problem with that is, of course, there's going to be some introduced, we might actually introduce some error into the control data set that way. And it's also hard for us to adjust along track. We're going to be working on some algorithmic improvements coming up soon that will allow us to basically do a non-rigid transformation. That will allow you to do maybe a longer linear corridor, and we'll be able to actually hold points fixed along the corridor and adjust to those. Right now we don't. So in a case like this, we might have some distortion along track. And right now you're just going to fit to the control in the end. And we might have this hump or kind of this adjustment in the middle that's really not going to be aligned properly. So we are working on this to improve, but just note that these are some challenges we've got with linear projects is we do need texture, we do need vertical features, we need good GNSS, and then where you place your ground control does have some challenges of where we put them as well. So I've got a few minutes here. I'm just going to kind of show you a couple of examples here. I'm going to walk into a linear corridor example. I will open up my browser here. We'll actually be able to show a data set, but I'll walk you through. This is one site that I've done that I kind of use as a test facility. It allows us to show a few different ways of collecting data. And I'm just going to kind of show you what we're basically seeing with these different types of capture that we're doing. So With this, I've got an example where we did just a single pass kind of around. This case, we did kind of a double pass around it. And I've got another one where we did like the really high density. The same GCPs in all the data sets, and we're running a local base on all of them. And in the end, we've got really, really good GNSS data. We're getting about 90% plus fixed certified positions, which is really good for what we want to see in our data set. But I'm going to just stop sharing this here quickly. Stop sharing, and I am going to jump over to share my screen. And I'm just going to optimize this for video. So what I've got, this is the one, that same example we were kind of looking at, it's really doing a really, really dense capture. You see I've kind of walked down the middle of the roadway and thing here, but as we kind of look into the data set for this, if I turn my point outline on, we get some really, really tight density when we're looking at the data. So it's going to load more data as I'm coming here. But you see that like your curb and gutter is very clean. We've got a lot of data. We've got every little nook and cranny. I've got a lot of coverage around like the bullnose of this curb. I can see my control point really well. So this is really where when you do a really, really dense capture, this is kind of the data that we're going to be seeing. In the case of what I did is I also did this one as just a double pass. So in this case, we did this one a little bit differently. Oh, sorry, let me just turn the double pass one on. I'm not sure my image is on. In this case, we only walked around the extent of the data. We did some loop closures in a few spots here. So we'll get a lot of density on the curb lines. But if we actually look at like the center of the roadway, this is really where we still are going to get some really nice data for like the road surface itself. And it's going to be quite precise on its own, but we're going to lack some detail kind of as we get further away from the camera. So this is something to consider here too. Is like I might not, because I didn't collect the center median, I just might not be getting the data I care about. So we saw some gaps in our data. You know, I can't see the backside of this curve very well. So I think that's kind of a challenge we've got with that overlap. We want to make sure that you see the data from as many locations as you can. You do notice that we were able to go a little bit further just because, of course, we are able to capture longer because or not capture longer, but capture a larger area because we don't have the same overlap we're after. But that's something we just got to be cautious about how much you can do for the density you're after. And then the other one, if we look at just doing like a single pass, turn this one back on here, you can see that I've now done even a larger area, but I've just done a single path all the way around. But now this is where I will be lacking even less density than I was getting before. The quality overall is still going to be quite high because I've got good GNSS. I'm generating my data that's going to be decent, but like I said, it's just you might not get what you're after. So keeping this in mind is if you care about features that are farther away from your capture path, then it's just going to be a bit problematic. You want to make sure you're doing the collection to get the overlap, get the coverage, get all this density you're after. It's really just going to kind of help out in the grand scheme of things. And then also the quality of your data is going to it's going to be a little bit lower and lower, even from the accuracy standpoint, if I push this a little bit more. The benefit, though, is I've done a much larger area in one scan, but it's kind of a trade-off. If you want really, really high quality data, you need to spend more time to get some higher density. So that's all I've got here now, but I'm going to jump back to our presentation just to kind of close some things off. This is normally when I hand it over to Teresa to kind of handle, but she's at a conference right now, so she's might be out of commission a little bit. So little announcement here. Our next webinar is going to be February 17th, and that's going to be about working with Looq Data in Trimble Business Center. So we're going to talk about how to use our Q survey tool, bring data into the application and be able to start generating kind of your field to finish data, creating some surfaces off of our data in TBC. It's just one of the products that works really, really well to bring our data into. We also have the upcoming user conference. Check out the website here. I think Teresa was going to send some things in the chat. If not, you can go to looq.ai user conference, and we've got early bird pricing for the conference until February 25th. So we're looking to have people join. If you're excited to join us down in San Diego from May 5th to 7th, you can check that out. And we'll have other webinars kind of coming up from here on out as well. So that's all I've got for today. So if anybody does have any questions, I know it's a small group here today, but if anybody has any questions, feel free to just type them in the chat or put them in the Q&A. I see Richard had a question, but he retracted it. So let's kind of close things up here if anybody's got anything to add in. All right, well, give everyone about 20 more seconds. And if you have nothing, then we'll end the webinar for this week. And you can join us on February 17th, the next one with TPC. Perfect. All right. Well, thank you to everyone who joined here today. I appreciate it, and enjoy the rest of your day. Take care.